So welcome to the IIT Bombay Virtual Competitive Algebra Seminar. Very happy New Year to all of you. Today we have with us Suprajo Das from Chennai Mathematical Institute. Suprajo will speak on an inequality in mixed multiplicities. So over to you, Suprajo.
Thank you for the invitation. I'm very glad to talk about this recent paper of mine, and the purpose of this talk is to talk about generalized Minkowski inequality in mixed multiplicities for filtration. Okay. All right. So I guess the first thing to do would be to recall the definition of filtration. So let's take R to be a Noetherian local ring, In a sequence of ideals in R, and we say I is a filtration if these following conditions are satisfied. Well, it's a filtration by primary ideals. So the first condition is that we require all these In for n bigger than or equal to 1 to be in primary. And we also require this In to form a descending chain of ideals in R, with I not being R. And the third and the most important condition is that if you take the product of I and Ij, it's going to land inside I plus j. Okay. And the filtration I is said to be Noetherian if, as one would suspect, this graded algebra direct sum In, it's a finitely generated one. Or in other words, this direct sum In, it's a Noetherian ring. Okay. Now, let's see some examples of imprimary filtration. The first one is the most classical one. So if you are in a Noetherian local ring R, fix some imprimary ideal I in R, and then simply look at powers of that fixed ideal. Okay, that forms an imprimary filtration. Another naturally occurring example of filtration in commutative algebra comes in the following way. So if you have two Noetherian local rings R and S, right, such that S dominates R, meaning that R sits inside S, and if you look at the contraction of the maximal ideal of S to R, it gives you the maximal ideal of R. Okay. And then in that case, one can define this filtration as follows. So the nth piece is the contraction of the nth power of the maximal ideal S to R. Okay, and this is a filtration by imprimary ideals. Now let's try to determine which among them is Noetherian and which is not. So in the first example, where you simply take powers of a fixed imprimary ideal, that is always going to be Noetherian. In fact, if you look at the graded algebra direct sum I to the n, the Riesz algebra, that's in fact generated in degree 1, right? Now in the next example, where we look at this intersection of powers of maximal ideal of S with R, this are oftentimes not Noetherian. Okay, and in fact, even in very nice setup, for example, if you take R to be some excellent regular local ring and take S to be some a discrete valuation which dominates R, even in such nice setup, one can construct examples where this doesn't turn out to be a Noetherian filtration. So, okay, so this is what we just discussed. All right, now let's start with the very classical notion of multiplicity, the Hilbert-Samuel multiplicity. Okay, so the basic theorem is this. So if you have a Noetherian local ring R, let's say dimension D, and fix some imprimary ideal I in R, then this length function, which associates to every positive integer n, the length of this Artinian local ring R mod I to the n. This function for large n, it behaves like a polynomial in n of degree d with rational coefficients. Okay, and this polynomial, it has got a name. It's called the Hilbert polynomial of I. Okay, so related notion is what's called the Hilbert-Samuel multiplicity. So you take this polynomial and write it in this following manner. So you have some leading term times n to the d, and you write the leading term as ei colon r divided by d factorial. And then you have some lower degree terms, okay? And this e of I colon r, this invariant, is called the Hilbert-Samuel multiplicity of R with respect to I, okay? Now a very natural question to ask is whether this theorem about eventually polynomial-like behavior of this length function, can it be generalized to the case of filtrations? Okay, but the answer is unfortunately no. Okay, and one can come up with a very simple counterexample like this. So one simply takes R to be a path series ring in one variable over some field K, and you define this M primary filtration in the following manner. So you let In to be this principal ideal generated by x raised to, so it's this function. Sorry, this is not what I meant. This function, ceiling of n times square root of 2, what it means is you take the smallest integer which is bigger than or equal to this number n times square root of 2. Okay, and this function in mapping to ceiling of n times square root of 2, it doesn't have eventual polynomial growth. In fact, even for large n, it doesn't even behave like a piecewise polynomial function. Okay, so so what we actually hope cannot be generalized to the case of filtration. Right, but this Hilbert-Samuel multiplicity can also be written in the following manner. So you take the limit of length of R mod I to the n divided by n to the d, multiply by some normalizing factor d factorial, and then take the limit. Okay, and the reason this limit exists is because of the fact that this length function in the numerator, it behaves like a polynomial for large n, it behaves like a polynomial in n of degree d. Okay, and writing the Hilbert-Samuel multiplicity in this way, it has a scope of being generalized to the case of filtration. Okay, and one can in fact show that these invariants are not only rational numbers, they're in fact positive integers. Okay, so this is a theorem of Minkowski, where he proves that, well, let's take a Noetherian local ring dimension D and let In be any M primary filtration M primary filtration of ideals in R. Then this limit length of R mod In divided by n to the d, this limit will exist for all such filtrations if and only if the dimension of the nil radical of the completion is less than d. Okay, so this gives a necessary and sufficient condition for limits of these kind to exist. Okay, so what are some examples of rings where this limit exists? So this will exist if R is an analytically unramified local ring, meaning that the completion of R has no nilpotent elements. So in that case, the dimension of the nil radical of the completion will simply be 0. And this theorem will tell us that the limit will exist. But what is subtle is that this limit may not even exist for all domains, because Nakata has some examples of Noetherian domains where the nil radical of the completion has dimension d. And this theorem will imply that one can cook up some M primary filtration in that ring whose limit won't exist. Okay, but even otherwise, this is a fairly wide class of rings where this limit will exist. Okay, so mimicking what we did for the Hilbert-Samuel multiplicity, we're going to define this multiplicity of an M primary filtration with respect to R. Okay, so certainly we have to be in the situation where this limit will exist. That is, it's a Noetherian local ring dimension D with this added hypothesis on the dimension of the nil radical of the completion, right? And we require that to be less than D. So in that case, we define the multiplicity of the filtration I in the same way defined for the case of ideals. Okay, and the point is, unlike as opposed to the usual Hilbert-Samuel multiplicity, which is always an integer, the multiplicity of a filtration can take any positive real number. Okay, and this can be done by simply modifying an example which we did a couple of minutes back. So you take alpha to be any positive real number, you take R to be this polynomial, the power series ring in one variable over some field K, and you define this in primary filtration in the following manner. So where this In is the principal ideal generated by x raised to the ceiling of n times alpha, right? And one can show that this limit, this multiplicity of this particular filtration will be alpha. Okay. All right. Now, this whole theory of Hilbert-Samuel multiplicity, which involves only one M-primary ideal, can be generalized to include the case of finitely many ideals. And this is called the theory of mixed multiplicities of ideals. And this was done by, so this came out as a result of cumulative effort of several mathematicians, and some notable ones include Bhattacharya, David Rees, Barnard Tessier, and Rizzler. Okay, so this is one of the fundamental theorems in mixed multiplicity of ideals. And so if you have a Noetherian local ring, dimension D, and this time let's take a finite number of primary ideals I1 through Ik, then this function, which maps this tuple N1 ... Nk to this particular length function, length of R mod I1 to the N1 ... Ik to the Nk, right? For large N1 ... Nk, this is going to behave like a polynomial in k variables of total degree D with rational coefficients, right? So if you take simply k to be 1, that just gives you the theorem for Hilbert-Samuel multiplicity. Okay, and this polynomial, it has a name. It's called the multi-graded Hilbert polynomial of I1 through Ik with respect to R. Okay, and a very nice reference for mixed multiplicities for ideals is this wonderful book called The Integral Closures of Ideals, Rings, and Modules by Craig Hunicke and Irina Swanson. Okay, in fact, chapter 17 of that particular book deals with this theory of mixed multiplicities. So whatever we are going to do for the next couple of slides, I'm going to refer to the notations from that particular book. So I guess it's good to see at least a sketch of the proof of why this length function behaves for large N1 through Nk, behaves like a polynomial, of total degree D for Nk variables. Okay, so this is the proof that is given in the book is based on the existence of what's called superficial elements. So let's recall the definition of superficial element. So let R be a ring and I be an ideal in R. So we say X in I is a superficial element of I. If you can find some integer C such that this colon ideal, that is set of all elements in I to the C, which maps X into I to the n plus 1, is precisely I to the n for all n bigger than or equal to C. Now one can easily see that I to the n, of course, multiplies X into I to the n plus 1 because X lives in I, right? But what this is saying is that there cannot be anything extra. Okay. Next theorem. This is a theorem about the existence of superficial elements under reasonably general conditions. So let's say you have a Noetherian local ring R such that the residue field is infinite, and assume that the dimension of R is bigger than or equal to 1. And let I be an primary ideal in that ring, and then one can find an X which lives in I but not in any minimal prime, such that X is a superficial element of I. Okay, and this theorem is very useful in the theory of mixed multiplicities for ideals because it provides a pathway for induction to work. Okay, now using this theorem, we'll try to sketch a proof of the asymptotic behavior of the multi-graded Hilbert function of ideals. Okay, first off, we can pick a superficial element. The reason we can do it, well, as the theorem says, you need the residue field to be infinite, right? But there is a standard trick in commutative algebra where you pass to this extension. So you take R, you go to this extension, R adjoin some indeterminate T localized at, sorry, don't have enough space. Okay, so this is a faithfully flat extension, and this is going to have an infinite residue field. And also the mixed multiplicities won't change when you pass to this extension. Okay, and of course you can assume the dimension to be bigger than or equal to 1, because if you are in dimension 0, it's an Artinian local ring, and the length will be eventually constant. Okay. Now, then it gives rise to an exact sequence of finite length R modules. Now, this exact sequence is true for any arbitrary integers n1 through nk and for any x. But the reason we are picking a superficial element is because for this isomorphism to hold, okay? And this module is independent of n1 through nk, okay? And then one has this equation of length, right? Okay, and now where this R bar and I bar, well, R bar denotes the quotient ring R mod X, and I bar, they denote the images of the ideal in the ring R mod X, okay? And now one can apply induction here, is because we have dropped the dimension, right? So then this function is going to behave like a polynomial in k variables of total degree d minus 1 for large n1 nk, right? And this is just a constant because it's independent of n1 through nk, right? And from this statement, one can get what we want, okay? So one simply has to add all these terms by varying n1. Okay. All right. Now, mimicking what we did for the Hilbert-Samuel multiplicity, right? We can write this multi-graded Hilbert polynomial, which is going to be a polynomial in k variables of total degree d, in this following way, right? We have this homogeneous part of the highest degree, and then some lower degree terms, okay? And these e of I1 raised to bracket d1 dot 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 ik raised to bracket dk, we call these invariants the mixed multiplicity of R of type d1 through dk with respect to I1 through ik, right? And it almost immediately follows from this definition that, well, if we take the case of a single ideal, then E I colon R, this denotes the usual Hilbert-Samuel multiplicity of I. This is equal to, according to our new notation, this is going to be equal to E of I raised to bracket D colon R. Okay. And if for some reason one of the DIs they turn out to be 1, we're simply going to drop that. Okay. That's our convention. All right. Now one can check that if one looks at this length and then take the limit by making m go to infinity, this is going to give us the homogeneous part of the highest degree of the multivariate Hilbert polynomial P, right? And writing it in this way, we're writing this in this way because this can be generalized to abstract and primary filtration. In fact, this whole theory of mixed multiplicities of ideals has been generalized to filtration by Minkowski, Sarkar, and Srinivasan. So one of the fundamental results, what they prove is that they're able to give a corresponding analog of this statement for ideals to the case of filtration. So let's say you have a Noetherian local ring R, dimension D, with this condition that the dimension of the nil radical of the completion is less than D. And of course, we need to have this condition because otherwise this limit may not even exist, right? And then one can show that for large, and one can show that for all n1 to nk, this multi-graded Hilbert function of these filtration divided by n to the d and then making limit n go to infinity, that's going to behave like a homogeneous polynomial of total degree d with real coefficients, okay? And the proof is quite involved, but let me make a few remarks about their proof. Okay? The first thing that they do is they first prove it for Noetherian filtration. And the reason they're able to get it for Noetherian filtration is because of a structure theorem. So the Noetherian filtration, they closely resemble the standard filtration. So there is this theorem in Bourbaki, which says that if you have a Noetherian local ring R, and if you take I to be any well, there's a typo. It should be a Noetherian in primary filtration. then one can find an integer a such that one has this identity, right? And if you simply take r to be 0, one gets that IAN is equal to IA raised to n. Okay, so once we have this Noetherian filtration, one can associate this standard filtration in this following manner. And then the hope is to use the results for standard filtration, and then using the structured theorem, lift those results to Noetherian filtrations. And that's exactly what they achieve. So this is what they prove. So with the same hypothesis, you do not even require the hypothesis on the nil radical of the completion. This works for arbitrary Noetherian local rings. Okay, so this says that that we have this equality. And if you look at the term on the right, it's a statement about mixed multiplicity of ideals, right? Okay. Now, how do they extend it to arbitrary ideals? They introduce this notion of truncated filtration. So this can be thought of as successive Noetherian approximation of arbitrary and primary ideals. So the definition goes as follows. So if you have any primary filtration in R, the eighth truncated filtration is defined in this following manner. So for the first A terms, you stay as it is, and then from the A plus 1th term onwards, you generate it by using the first A terms, right? So so as you vary A, as you increase A, you can think it of as an approximation of your original filtration. Okay. So the next theorem that they have is this. So this is where you need this additional hypothesis that the dimension of the nil radical of the completion is less than d. Then in that case, you have this equality of limits. Okay. And well, by the I subscript A, I mean the truncated filtration. So you look at this length, the multigraded Hilbert-Samuel function of the truncated filtration. Then you look at this limit and then make A go to infinity, and that would be equal to the multigraded Hilbert-Samuel function of the original filtration. Well, the fact that these limits are going to exist and that they'll be equal is quite deep, and it's based on the idea of volumes of Newton of uncurved bodies. Okay. All right. And mimicking what we did for the mixed multiplicity of ideals, we generalize the same definitions. They generalize the same definitions to mixed multiplicity for filtration, right? So you look at the highest degree part, and then you write it in this following manner. And these invariants, right? It's called the mixed multiplicity of R of type D1 through dk with respect to these and primary filtrations I1 through Ik, right? Okay. All right. Now, this is one important result about mixed multiplicity for ideals. So this is a theorem of Risler and Tessier. What it says is that if you are in a suitably nice ring, then one can quotient by superficial elements, and the mixed multiplicities won't change when you pass to the quotient ring. Okay, so if you are in a Noetherian local ring R, whose dimension is bigger than or equal to 2 with infinite residue field, let's say you have some imprimary ideals in R, then of course in this setup one can pick a superficial element, and then one has this nice identity of mixed multiplicities. Okay, so again here by R bar I denote the quotient of R by X, and by I bar we denote the images of I in R bar. Okay, and again the proof of this is very similar to how we proved the theorem about the multigraded Hilbert polynomial. Okay, and this is going to be useful later on when we try to generalize these Minkowski inequalities. Okay, now in mixed multiplicities for ideals, we have these nice set of inequalities about mixed multiplicities. which are called the Minkowski inequalities. So Minkowski, I think he originally had them in the realm of convex geometry, and then Tessier realized that they can be transferred to commutative algebra. And then, but I think he had some extra assumptions he assumed R to be Cohen-Macaulay. But then Rees and Sharp, they were able to generalize them to arbitrary Noetherian local rings. Okay, right. And in the same paper where Katkowski, Sarkar, and Srinivasan, they introduced this notion of mixed multiplicity for filtration. They, in fact, they generalized almost all the general theory of mixed multiplicities for ideals to the case of filtration. And this is one of the theorems which appears in the paper. So they were able to give the exact filtration analogs of those Minkowski inequalities. Okay, but all right. So if you look at the third inequality, this has a scope of being generalized. This can be generalized to an arbitrary number of ideals, not just for two ideals. Okay, so this theorem does precisely that. So if you have Noetherian local ring of dimension D, we have this inequality. Okay, and I found this inequality in not in any commutative algebra book, but in the algebraic geometry book called Positivity and Algebraic Geometry by Lazarsfeld. And he sort of indicates how this can be done, and this is based on an inductive proof by superficial elements. Okay, so this is how it goes. So first off, it's enough to study multiplicities of this type. It's because by allowing repetitions, you can realize this multiplicities in the following manner, right? So it suffices to prove this inequality, right? Okay. Then again, we can assume by the standard trick, we can assume that the residue field is infinite, and we can assume that the dimension is bigger than or equal to 2, because if the dimension is 2, it's already if the dimension is 1, it's trivial, it's actual inequality. Okay, and then in this case, by using the result by the theorem of Rissler and Tessier, I can find a superficial element such that all these identities hold, right? Okay, so once we have this, sorry. Okay, right, and then we have this series of equalities and inequalities. So the first step, this comes from the identity that we just wrote, because if we quotient out by superficial element, this mixed multiplicities won't change, right? And then since we have dropped the dimension, I can induct on the dimension. So this inequality, this inequality, it comes from the inductive hypothesis, right? And then this one, this comes from, well, it's the identity that we just wrote. It's the theorem of Rissler and Tessier, right? And again, here we're applying this inequality to each term in the product. And this is true because we have the inequality for two ideals. That was already done before, right? And I guess this one is just rearranging those terms. And then our desired inequality follows by raising both sides to the power d over d minus 1. Okay, so that gives us what we want. Okay, now using the results of Katkowski, Sarkar, and Srinivasan, I think almost without modification, we can give a filtration analog of this generalized Minkowski inequality. So I'm going to see a few lines about how this can be done. So the first thing to do is to first prove this inequality for the truncated filtration. So you replace each of these filtrations by their truncated ones. And since these truncated filtrations are Noetherian, right? So by using the structure theorem for Noetherian filtration, for every, so we can get an integer FA large enough such that this works, right? And then you can associate a standard filtration to each of these truncated filtration, which are called this JA of I, right? And we already know that the inequality is true in the case of ideals. Okay, and now using this their results, we have these equalities, right? And the inequality is true for these GIs because these are ideals, right? So this proves it for the truncated filtration. But then the point is, once we have this inequality for truncated filtration, the hope is to take limits by making A go to infinity and prove it for arbitrary filtration. And that indeed works, because this is what this Newton-Acunkov body achieves, is that you can do that. Okay. All right. So one very nice consequence of this generalized Minkowski inequality is that, well, there is a result by Katkowski, Varma, and Srinivasan, which says that, which talks about when do these mixed multiplicities when are these mixed multiplicities positive and when are they zero. So, for example, if we are in the situation of an analytically reducible Noetherian local ring, meaning the completion is a domain, in that case, this mixed, and if you suppose that the usual multiplicities of each of the filtrations are positive, then the mixed multiplicities will all be positive. And if you assume that one of these multiplicity of a filtration is 0 for some j, then the mixed multiplicity will be 0 for all these di's, such that their sum is d and the dj is non-zero. Okay. Now, both of these proofs, they're based on this idea about volumes of Newton-Acunkov bodies. But the second part of this theorem, which talks about when these multiplicities are 0, the second part, that's a direct consequence of this inequality, right? Because you simply have these upper bound, and if this if one of these terms is non-zero with dj being positive, then it forces this mixed multiplicity to be 0. Okay, so that can be recovered by making use of this generalized Minkowski inequality. All right, so I guess I spoke too fast. I think that's all I had for today.
Okay, so thank you, Suprajo. We can take questions.
Sure.
Suprajo, I have a question.
Sure.
Yeah, so I guess one obvious question will be that once you have this inequality, the
Right.
Minkowski inequality, one would want to know under what conditions do we have equality.
Oh.
So for two ideals, we know what happens, but have you experimented with the multi-ideal case?
Not really, but I guess that it might be related to a question in integral closures, because usually these equality of multiplicities has got something to do with integral closures, but I do not have a concrete answer to that.
Okay, but what is your hope? Like, have you experimented with it?
Well, I really do not know. I think if you take a different inequality, for example, the fourth one, I think Katkowski has some result in a very recent paper of his, but I really do not know what happens for the third one.
Okay. Yeah, thanks.
Thank you.
I mean, given any filtration of M primary ideals, one can pass to another filtration where you simply take the integral closure.
Okay.
Then in the usual theory, the mixed multiplicities don't change.
Okay.
So
Yeah.
suppose since everything comes down to Noetherian case, which when it should be okay. I mean, ultimately, one should be able to use the classical result about equality related to integral closure to get this for
I see.
filtrations also.
I see.
So all these results, the strategy is to reduce to Noetherian case by truncating the filtration, and then Noetherian case can be reduced to ideal case. In the ideal case, we have integral closure. If the two filtrations are integral closures of each other, then equality holds.
Right. Right.
So
Okay.
I believe it should be true, but I have not seen a proof written down.
I see. Yeah, that might be an interesting area to pursue.
Right. So here you mentioned the inequality whose proof you found in
Yes,
other
I didn't.
book.
Yeah, I didn't find the proof in any commutative algebra. I was glossing over Lazarus's book, and I found this interesting generalization of this, one of the Minkowski inequality. And I think they refer it to as the Hodge inequality.
So their proof is geometric.
They have a geometric proof, but one can very easily transfer that idea to commutative algebra.
Okay.
It's almost immediate.
Mm-hmm. Yeah, any other questions? Yeah, I have a question which pertains to how I got into mixed multiplicities due to a result of Craig Hunicke and Judy Sally, where they looked at Rees algebra of an ideal and localized at the maximal homogeneous ideal, and they had a calculation of its multiplicity.
Okay.
So its multiplicity they expressed in terms of mixed multiplicities. And so now suppose I take a arbitrary filtration, even Noetherian filtration, one can, the Rees ring is Noetherian,
Right.
and again localize it at maximal homogeneous ideal, whether the multiplicity is sum of the mixed multiplicities.
Okay.
So I have not seen this application yet for the general theory
I see.
of non-Noetherian filtration.
I see. I see.
Yeah, one can construct the Rees algebra and localize and ask for its multiplicity. And
Right. Yeah.
even one can look at the fiber cone, and its multiplicity is also related with some of the mixed multiplicities. And I don't think that is also known.
Yeah. So, yeah. Maybe those are interesting things one can look at.
Yeah. Okay, I guess I don't see any further questions. So Suprajo, thanks a lot for your very interesting proofs of this very involved theory in notation, but it is clear many times what to do. So thank you very much for coming online.
Thank you.